We will continue with our preliminary comments on helicopter aerodynamics and performance. In our last recording, we talked about the many problems that the helicopter aerodynamics is involved, and how many disciplines such as aerodynamics, structural dynamics, flight dynamics and control, and aeroacoustics have to work together on it. And we also said helicopter is a unique vehicle in that the main rotor is the primary mechanism for producing not only lift but also thrust for propulsive forward motion and also for the rolling motion and pitching motion. So a lot of the control also authority comes from the main rotor itself. And we said we need a systematic approach, starting with back-of-the-envelope approaches, spreadsheet or MATLAB-based approaches, then CFD, then you do some wind tunnel testing of scale models, then you do flight testing. So there's a sequence of processes by which aerodynamic vehicles, aerodynamically efficient helicopters are developed. So this particular course, we are going to have several parts to it. So roughly there'll be a quiz after each part. So the first part would be power prediction. What happens when the helicopter is standing still? How much thrust can it produce? How much power is it able to produce? How do the lift and drag vary from root to tip? How can I design it? How can I analyze it? These are all in hour. Then in the second part, we are going to talk about a forward flight of the vehicle. How do I control it? What happens to the blade dynamics? How does the angle of attack change? What are the lift and drag all along the rotor? How do I compute it? How do I compute thrust, power, pitching moment, rolling moment, everything right at the center of the rotor disc, which is called the hub. So when we finish part 2, there'll be a second quiz based on that. Then we'll talk about helicopter performance. How do I compute the range? How far does it travel is called the range. Endurance, how long can it stay up in the air? How much fuel do I carry? How much fuel am I going to burn? And if I'm doing a special maneuver such as a dive turn or a steady level turn, how do I compute the performance of the vehicle? Then there'll be a third quiz. All of these will be posted online, and then you'll be working on it and submitting it online. And then the fourth part is just a background info, fourth and fifth part. So there won't be any quiz or an exam. So the last 2 or 3 weeks of the course, we will cover topics 4, and 5. So we will cover 1, 2, 3 and give you enough time to do the quiz after each part is done. While you're working on the quiz, we'll be covering the lecture material for the second part, and then the third part, and so forth. The textbook is, if you want to buy a book, I recommend Wayne Johnson's first edition. It's less than $25. You could also use Gordon Leishman as a reference. There are other books by Prouty, Gesson, Meyer, Stepnevsky, and Keyes, but you do not need to buy these books. I will try to do my best to provide you all the slides, some Word documents, some PDF files as part of this course. As I mentioned to you, there's going to be some homework assignments. There are going to be a total of 3 quizzes, week number 5, week number 10, and week number 15, something like that. Everything is take-home exam. Either you use an Excel spreadsheet or a short MATLAB program that you'll write. Honor code is very strictly observed because you're doing the work on your own. I'm giving you a lot of time, but you are not required, or you are not asked to consult with anybody else. You have to work by yourself. You cannot work together on projects. You cannot work together on homework or exams or exchange computer programs, things like that. Any collaboration would be considered a violation of the honor code, and you'll be asked to drop the class or receive a failing grade. Again, everything will be submitted electronically online. Even for homework, you will have a PDF file describing your methodology, describing your results, plus a separate submission of either your spreadsheet or your MATLAB code. Okay, so nothing will be handwritten in this course. Everything will have to be typed up. You can certainly cut and paste the equations and things like that from my notes. That's no problem. Again, this is my email address. I hope to have some regular Blue Jeans sessions where we talk to each other. If you need to contact me, send me an email and set up a time. Then we can talk either on the phone or on Blue Jeans. Now we are going to briefly talk about the history of the helicopter. The earliest helicopter that is known is called the Chinese top that you have seen. It's a children's toy made of usually of wood. It's got a rotating blade-like structure up on top with a handle. You spin it with your handle and release it, and then it'll float up for a while, spin for a while, then crash. It had two limitations. It was able to produce the lift, the rotor, but there was no sustained power being supplied to the rotor. Therefore, when it lost all its energy due to friction and due to induced drag, then the rotor came to a stop. Also, it was not possible to control with the trajectory, although you practiced. If you practice hard enough, you may be able to direct it in a certain direction. But once it leaves your hand, it's at the mercy of the prevailing wind, the room conditions, and anything else, any other obstacles in its path. Leonardo da Vinci thought it may be possible to have a rotating wing like the Chinese top, except it is powered by some kind of a mechanism. There you could see some shaft that's spinning the upper. These two blades are two rotors. He had at that time also a foil or a sail plane, like a thin fabric-like material for producing or creating the wing. And then there were some gear-like mechanisms, but the picture kind of stopped here. Leonardo da Vinci did not explain how you would power it. Of course, people have thought when they saw this picture, perhaps I can use a human power to power this particular system. It turns out it's very hard to do. So let's say that you are a normal 160-pound person, and you're using a rotor like this one, and you're physically, making it rotate perhaps with a bicycle-like mechanism, pulleys and wheels and gears. Somehow you generate a rotating motion of the rotor. You're using a rotor radius, let's say, of 6 feet. The rotor disk area is pi r squared, so roughly 100 square feet. Density, there's a typo here, it should be DEN, pardon me about that. It should be DEN. DEN-SITY. Is in slugs per cubic feet. One of the back of the envelopes relationship we will derive a little bit later using a theory called the actuator disk model gives you this formula. So this is the lift you want to produce, that's W, in this case it's 160 pounds. This is rho is the density of the atmospheric air, the operating density. A is the disk area, which is pi r squared. Then it's an ideal power, neglecting viscosity, neglecting many losses in the system. You get already a 5.33 horsepower. It's very hard for a human being to produce so much horsepower on a sustained basis. But in reality, you have other losses in the system, skin friction losses, so all kind of other things we will talk about. Therefore, the actual power works out to be much higher than this 5.33 horsepower. So it works out to be 6.7 horsepower. The ratio between the ideal power and the actual power is called the figure of merit. We will later on develop very precise ways of estimating the figure of merit, but we are assuming a figure of merit of roughly 80. That means 80% efficiency, if you will. So you could see that a human-powered flight is not very convenient, not even possible on a sustained basis, because it's very hard for a human being to generate this much horsepower. If you want to reduce this horsepower, you can either increase the area, which means you need a very large radius rotor. But if it's a very large radius rotor, it's going to be very heavy. Otherwise, it's going to droop like a willow, like a plant. It's going to drop. It won't maintain its rigidity unless it's a rigid rotor. Also, if you are at a higher altitude than the sea level, this is the sea level density. When the density decreases, the power requirement goes even more high. So one of the design conditions for helicopters is on a hot day, that means the temperature is high, P equal to rho RT, therefore rho is low. Out of ground, that means you are not taking advantage of the ground effects to kind of hover over the ground. At high altitude, sufficiently high altitude, so the density is low, rho is low, then your helicopter should be able to hover. This is because Army found it the hard way that when they were operating in Afghanistan and Iraq and other mountainous regions, very often they ran out of power. So density affects it, disk area affects it, of course the weight also affects it. So human power is not possible, so people started looking at other machine concepts. Damicourt in 1863 proposed a steam-propelled helicopter. As you know, Industrial Revolution took place when James Watt found the power of steam. Then Robert Louis Stevenson built a steam engine, railroads were constructed, and so forth. So Damicourt said, why don't I use the steam power, push a piston up and down, and somehow convert the linear motion of the piston into circular motion, just like we do in our car, rotary motion, and let the rotary motion rotate this particular propeller. So he even got a patent for it, but this was not very practical because steam engines were very heavy. Therefore, this one never got off the ground as far as I can tell. But the science fiction writer Jules Verne was very impressed with this particular idea. So he even wrote a couple of science fiction stories where people used a helicopter. And the word helicopter apparently was first coined by Damicourt, the Frenchman. As later on, people went from steam engine to piston engines. As you know, by 1900, 1900, cars were being built. Henry Ford was building piston engine cars. They were rudimentary, petrol or diesel-powered cars. So Paul Carnot, a Frenchman, in 1907, had a small 14 horsepower piston in a multiple cylinder engine here, stacked one after the other. It was very heavy, and the horsepower was relatively small. By the way, if you go to this Wikipedia, you'll see the same picture, and then you'll also see some examples of the this is a better looking picture. You can see the piston engine, 1, 2, 3, 4 cylinders. This is the crankshaft. Then there's some gear mechanism that causes the rotor to rotate. And the engine was a 24 horsepower engine. It weighed almost 600 pounds. So it was very hard for it to fly more than for about 30 seconds or so. It could go only about 7 feet, so it could hop and down, up and down. So it was not able to fly. Okay. So this was the next helicopter that is attributable to Carnot in France. 1903, Wright brothers had already flown and controlled the flight of an airplane. So helicopter was not there yet. But not too long after that, around 1923, By the way, before that, Sikorsky was in Russia. He was doing other things. We will refer to his work in a later slide. Sierva said, I'm going to use a regular airplane-like structure. So I'm going to use an airplane propeller to propel it forward. But instead of a wing for producing lift, I'm going to use a rotor here, except it operates like a wind turbine. It'll be tilted slightly back, so when the wind hits it, it'll start spinning, then it'll produce lift. But because it's tilted a little bit aft, it will also have its own drag in addition to the fuselage drag. So De La Sierva found that this vehicle called autogyro was able to maneuver at very, very low speeds. It still needed to need a running start like an airplane, but he did not have to go very, very fast before the wind started hitting the rotor and causing it to spin like a wind turbine. Then it produced the lift. Because of its ability to operate at very, very low speeds, it was also able to maneuver at very, very low speeds. When De La Sierva first built the models, they worked fine in a wind tunnel. But when he built actual blades using metal structures, he found there was an excessive rolling moment. Remember, we talked about very high dynamic pressure on the advancing side, very low dynamic pressure on the retreating side. So too much lift on one side of the rotor compared to the other side. The rotor was wanting to roll to one side, and it was trying to fail. Okay. Then he wondered, why didn't it happen in my wind tunnel test? What happened? So it turned out in the wind tunnel test, he had wooden structures. So wooden structure had some flexibility or a pliability. So the rotors were flapping, elastically up and down, relieving themselves of the excess lift by flapping. So he said, okay, now I don't want to use a wooden structure. I want to use metal blades, but I'm going to put hinges near the root so that the blades will freely flap up and down. So De La Sierva was the first guy to come up with the hinged flapping blades. Of course, the minute you put a hinge, if you have a 4-bladed rotor like this, you have 4 hinges, they collect dust. Just like your car needs to be lubricated, each one of these hinges need to be lubricated. They need to be inspected for cracks, failures, breaks, and so forth. More things can go wrong, and yet, more things may happen. Another thing Sierva found was when the blade was flapping up and down, it was also rotating. It generated a centrifugal force. It generated not a centrifugal force, Coriolis force. Coriolis force was pushing the blade back or forward in the plane of the rotor. The Coriolis acceleration is 2 times omega cross v. So omega vector was along the shaft, v was in the plane of rotation. So it was neither along the shaft. So it produced a Coriolis force. Coriolis force caused the blade to want to bend in the plane itself backwards. Instead of going vertically up and down above the rotor disc or below the rotor disc, it was moving back and forth. It's called a lead-lag motion. So he said, I'm going to put a hinge to relieve the stresses that are caused by it. So now you had, in addition to flapping hinges, you also had lead-lag hinges. Later on, we'll have some pictures of it when we talk about forward flight. We will show you how do these hinges look like and so forth. Anyway, Sierva was the guy who invented all of these things. It was also very unfortunate he died in an accident. So he is responsible for flapping hinges and also for lead-lag hinges. Then came Sikorsky. Sikorsky predated Sierva around the same time as Paul Carnot, except he started his work in Russia. Then he came to the United States. He's a guy who gave the helicopter the look that's similar to the modern helicopter look. There was a tail rotor back here. There was a main rotor here. You see these rods. These are the ones that pitch up and down and rotate the blade cyclically up and down. So they are called the pitch links. It was fully enclosed so that the pilot was protected from the natural elements. There was a visibility available, and there was some cargo room back in here. How was the tail rotor powered? He had a shaft that is running through the fuselage. In modern helicopters, this shaft runs through the tail boom, then connects it to the tail rotor. You may wonder, why do we need a tail rotor? This is the reason. So to rotate this main rotor, you have some kind of a gear, some teeth. So the shaft rotates. The shaft has got gears. The gears are connected to the propeller. Gears associated with the propellers. So the propeller, the rotor rotates. So when that happens, you are supplying torque to the rotor. Because the rotor resists that motion, an opposite torque is generated on the engine, on the fuselage. So your helicopter wants to rotate, okay, in the opposite direction to counteract that torque. So to overcome the torque, Sikorsky said, I'm going to put a rotor here. It's going to produce a thrust back here in the plane, perpendicular to the plane of the paper. Here is the center of gravity. Because of this distance, it's going to produce a torque. So the main rotor had a torque. To counteract that, the tail rotor was introduced. So Sikorsky was the first guy came up with this. As soon as he came to America, the American way is to patent it. So immediately he patented it. Then he was very smart. He realized that this vehicle could be used by military forces, Army for observation, Navy because this can get off a ship deck. So whether it's a search and rescue operation on the sea or looking for torpedoes or submarines or enemy ships, such a vehicle would be very helpful. So he went to the armed forces in 1942, armed services, and also Royal Air Force. He got an order to build a helicopter which weighed roughly 1 ton, 2,500 pounds. It used a 180 horsepower piston engine. Later on, after you prove something militarily, then you build a civilian helicopter. So the S-51 is a 4-seater civilian helicopter. It was produced under license by Westland Helicopter in England. It became the Britain's first helicopter. So this is Sikorsky's contribution to the helicopter industry. There are other ways of counteracting the torque, in addition to the tail rotor that we just talked about. You could have one rotor spinning one way, other one spinning in the opposite way. So this rotor, when it tries to resist the motion of the torque provided by the gears, produces one type of a torque on the structure. Here it produces the opposite torque. They kind of cancel. This is called a tandem rotor. This is the Chinook rotor. Notice that they would have to be not only horizontally separated from each other, but also vertically separated, so there is sufficient clearance between the rear rotor and the front rotor. Okay. You could also have a coaxial rotor, where top rotor is spinning one way, the bottom rotor is spinning in the opposite direction. Okay. This is Russians came up with it. Sikorsky now, this is their favored way of doing it. Their modern high-speed military helicopters they are proposing, including their Sikorsky X2, which set a world speed record, uses this concept. And then the Sikorsky helicopters have a propulsor in the back, which provides the forward thrust. The purpose of the rotor is primarily to produce a lift, nothing else. So this is a picture of a single rotor conventional helicopter with a tail rotor, McDonnell Douglas 500. This is a CH-47D, which is an example of a tandem rotor, Chinook rotor. Russian helicopter, comma. Notice the clearance between the upper rotor and the lower rotor. So you needed enough clearance. You needed two shafts, one spinning one way, other one spinning the other way. Very fancy gear mechanisms. He needed to pitch each blade up and down. So you needed two sets of pitch links, one for the upper rotor, one for the lower rotor. All of this exposed structure was very, very draggy. Remember I mentioned that the CD of a cylinder is 1. CD of an airfoil is 0.01. Therefore, this was a very, very draggy, system. But this is what the Russians came up with, KA-52. McDonnell Douglas came up with something called a no-tar helicopter. No-tar means no tail rotor. It used a principle called a Coanda principle that I will briefly describe in my following slides. So basically, it had an open area here. It sucked the external air and pumped it through a fan back here. The fan created a blowing air. Some of it came through back here called a residual outflow, like a side jet. But a lot of it came through slots on this region called the tail boom. Okay. So what does the tail boom do? This is the principle behind the Coanda jet. When a jet is blowing on a curved surface, it has a tendency, it does not go just straight away. It hugs the surface and follows the surface contour. This is called a Coanda effect. Therefore, this air that is coming from the fan, when it came out of these slots, this seesaw tooth-like slot over the boom, rather than blowing off the tail boom, it followed the contour of the tail boom. So when that happened, what happened was the jet came out of that from inside the tail boom. It followed the contour. It went this way. Therefore, this had an asymmetric behavior, asymmetric flow to the left and right. And this downward, number 6 that we see here is the downwash from the main rotor. So when the downwash hit this flow field over the cylinder that has been asymmetrized because of the formation of this jet, it produced a side force, just like a tail rotor will produce side force. Okay. So this picture comes from this particular site. Okay. So 1 is the air intake. This is the air intake. 2 is the variable pitch fan that is inside. This is the fan. 3 is the tail boom. This is the tail boom structure. 4 a vertical stabilizer. 5 is the directed thrust is coming out of here. This is the residual thrust. 6 is the downwash. 7 is the tail boom. This is the slot of the tail boom. Then the air comes out of it, follows the contour. This is the anti-torque lift that is produced sideways force, just like a tail rotor would produce a sideways thrust. Okay. So therefore it produces counteracting torque, counteracting the torque supplied by the main rotor on the vehicle. Another way you could do it is a tilt rotor. Then one spins one way, the other one spins opposite way. Then they produce also zero torque. Okay. As the helicopters gotten better, each generation of the helicopter would be a little bit heavier than the previous generation and would require a little bit bigger engine as a result. This is an Apache Helicopter 64A, the earliest version, built by McDonnell Douglas, now Boeing helicopter in Mesa, Arizona. This is AH-64D, which is a later version. Okay. Notice the length. Length is about the same. We want to keep the helicopter as compact as possible so that they could be stored inside a fuselage of an airplane and transported where needed, like a C-17 or a C-5. You disconnect the blades, remove the blades, and then put this inside the fuselage. So the length was about the same. Height actually got smaller, shorter, so that it could fit inside the fuselage. but it had a small subwing. Subwing is like a little wing sticking out of the side. You could use it for carrying external fuel tanks, some guided missiles, probes, velocity probes, radar sensors, you name it, sensors. They could be mounted on the subwing-like structure. It produces a small amount of lift, not much to write about. But when you go from version A to version D, the weight is increased because Army always wants, can I carry more payload, more soldiers, more computers, more weapons, more bullets, more missiles. So the requirements are always increasing. The weight is increasing. So if you do not change the engine, if you have the same engine, remember the power that we talked about depends on the weight, W times square root of W. So if the W goes up by 6%, then the power requirement goes up by 9%, 9 to 10%. Okay. So if you have the same engine, then you find you're not able to fly at high enough altitude. Remember, the density was in the denominator inside the square root. So higher altitudes are no longer possible. You have to settle for flying at a slightly lower altitude because this is a heavier vehicle. This is in-ground effect. That means you're taking advantage of the cushioning effect of the ground. We will see later on when we talk about vehicle performance in part 3, a little bit about the ground effect. If you are out of ground effect, that means high enough so that you cannot take advantage of the cushioning effect of the ground, your altitude decreases. Even for Model A, 12,000 feet, this is only 10,000 feet. On a standard day, that means sea level temperature, if you have a non-standard day, hot day, density will be lower, then you have even lower altitude. Instead of 12,600 feet, you have 11,200 feet. Same thing up here. In addition, you cannot vertically climb up or down because you don't have enough power to increase your center of gravity. I should say, increase your potential energy. Any rise in the potential energy comes from the engine, so engine does not have enough power. So Model A could rise up 660 meters per feet per minute, or 663 meters per minute. H64D was able to do only 541 meter per minute. So this is vertical rate of climb. In forward flight, if you're flying forward and also gaining altitude, it turns out you can climb somewhat more. Again, Model A had almost 900 meter per second. This one only had 800 meter per second. You're also compromising the forward speed. It's 279 kilometers per hour. It's 273 kilometers per hour. Cruise speed is reduced also. Okay, this is the performance. So when you increase the weight of a helicopter, the performance deteriorates. So we're going to look at our performance, first part of our course. Then we'll look at the forward flight performance, second part of the course. Then we'll look at how to estimate the performance in the third part of the course. So these are the things that we will be covering in this particular course. So early engines used piston engines. Piston engines are hundreds of horsepower. But as soon as turbine engines came about, at least for military purposes and in some commercial purposes, people went to turbo shaft engines. These are several $100,000 or tens of thousands of dollars, very expensive, but they have lots of power. Instead of tens of horsepower, hundreds of horsepower, they can produce thousands of horsepower. So they could do the mission for a variety of conditions. That's why Apache helicopter and also the Black Hawk helicopter and some of the helicopters and also the V-22 tilt-rotor helicopter use piston engine. And they use turbine engines, gas turbine engines, for producing the power that they need. So if you keep going faster, we have already seen shocks will form. retreating side of the blade will stall. You'll have a lot of vibrations because you're producing a high lift on one side, low lift on the other side. You're flapping your blade up and down, you're pitching your blade up and down. Dynamic pressure is increasing on one side, decreasing on the other side. Shock produces shock noise. Remember, drag is proportional to velocity squared, 1/2 rho velocity squared times CD times some reference area. So drag is proportional to velocity squared. Power is drag times the velocity. Therefore, the fuselage parasite power goes up as V cubed. So we need to be able to understand and accurately predict the air loads in high-speed forward flight. This is something we will attempt to do in this particular course. So to conclude this general introduction to helicopter aerodynamics, this is an interesting area. There are lots of problems. There are also lots of opportunities for innovation. So this course is intended as a starting point, not an ending point. So this is just a start point for you to explore and compute and estimate the performance of most modern helicopters. So we will stop this recording at this point.